Okay, so any questions? Let's open the recap. So what did we do last time? We can go first of the day. Seven point. Not another point. I never used the word 7 point. Right, relation. We looked at some examples of constraint and unconstrained components. It's not what we do. Connected to go back maybe for 5 minutes for you. So what was necessary? What was vision? What kind of functions? On compact domain. If you take any continuous function, then it will. The part of it. Okay. Put them aside. That's just one stuff then. But what would be necessary sufficient optimality? Write it out. There's a lot of integration to your remarks. Keep it out.
There's a local main if the derivative.
So we define something for local. So what is the necessary function that? Okay, what more?
Strictly positive. Yes, positive symbol positives definitely. No, positive definitely, not separate.
I don't think it goes positive there.
This local minimum they will apply, but for the converse, we need the
Local minimum.
implies.
Now what does it do?
We look at examples where it works, but we also look at it from where we can you say this I claim something and it will prove it wrong with the example. So why did it go wrong? The equality.
Just take over and apply. Yes. Okay, so we try to apply. Let's look at the AJ. Statement for the numbers. It's 1 through 11. Oh, so given whatever we learn, can it do this? The optimization is not only always going to come in the form of minimize. If you try to do an inequality of this sort, what could you do?
Take a particular function, we can take a given function from Rn to R, which is convex.
So we make specific minimum of AM minus DM is 0.
That's one way. You could just push this guy here with the minus.
and try to do that for whatever numbers xi unconstrained. So what would I do? Simply type a random which is this one. And now do a unconstrained optimally to minimize the conflicts. If that happens to be greater than 0, my inequality is satisfied. If it is not, then there is something wrong. So it's not always going to come in this form, which is very useful in proving inequality of this type. Something is less than something, or something is greater than something. We put a function that will minimize the maximum. If it turns out to be right form, you have to. Oh, so suppose you want to show this, what would you like to prove, and what have you learned from the last class? You can transform them, these exercises into something which is more useful. That's okay. That's not something you're going to use from last class. But what do we know for a function to achieve its minimum?
The domain should go back.
It's unconstrained. What do we- What is the first possible, first necessary condition we wrote?
The gradient is 0.
What else can it do? That's simple as that. So let's try to first transform that, such that you can. So what's the easiest transformation where these powers look like nicer functions?
Yeah.
Okay, so what should I do? Y equal to log x. Let's say y equal to log x. X will be e to the power y. Now what is this one? Y is the summation of
E to the power
e to the power
solution. Y and
where here
y and x solution
minus
solution e to the power y.
oh, what should I do now?
We can use the we have exponential function with the convex and increasing.
What do we do that overall convex increase?
If I just look
First
at
one, this part.
this,
Okay, why would that help you?
we can pick endpoints y1 yn in the domain, and we can take a non-trivial linear combination 1 by n, which is each one. So that is smaller than that, so that will be equal to 0.
So it's a differentiable function, so we just equal the gradient to 0.
Yeah. Be slightly complicated.
So this is, if I take the 3 by n,
This is minus or this is minus. That's also something we should tell. Should I take this minus this or this minus this? The way I learned is this minus this. And this is a less than equal to inequality. What can I conclude if I were to minimize this function?
Oh, nothing, it's nice.
That's the maximum. And so equivalently, you can either put a minus here. That's it. So let's try it. It's just let's put a minus on this. You want to show that the minimum value will be greater.
This is always equal to.
Already know.
I think my argument is right.
What is that?
So e to the y is convex.
Okay.
So we are taking y endpoints from the domain, y1 to yn, and we are giving the combination of.
So I don't want to use convex text for the moment. We did remove last time anything about complexity.
I don't know.
Can you do it without making convex?
About pages.
No. Just the necessary condition. What is the necessary condition for? To propose and play subdivision international quantity test. What is the optimality of that? It's fixed. What am I trying to maximize or minimize? What about just this part, anything fixed. So all I'm trying to do is to minimize. Okay. Now, if you want to solve for this, what we do? At optimal, what will happen? All the partial derivatives will zero. And I have this extra condition, so I would write this as an n-1 dimensional problem. Because I'll give a lot of equations, right? To solve it, it might be helpful to write yn as s minus. So let's just write yn as s. If each time I take the derivative of it with respect to y1 by what will I get? So now b, let's go. bg yes. What would this look like?
We were to the yj,
Sorry?
we were yj into e to the power minus. It will be e to the power yj minus e to the power minus y. Minus e to the power minus 1.
e to the power
Yj minus.
zero minus
Yeah, fine. Will. Minus e to the power minus 1. Summation y.
huh?
N minus 1 to power 5. There will be minus.
Here,
No, so before the summation.
here,
Before the summation.
which is
I less than n minus. Less equals to n minus 1.
Correct. Yeah, basically. So basically the second exponent is just yn.
all of this is just yn.
No, it should be s minus summation, so.
Okay. Whatever. If people following what is going on. What are we trying to do? That's the most important. We're fixing the sum of y's to be equal to s. And on that space, it's a subspace or hyperspace, whatever you want to call it. We're trying to minimize this function g. So what should happen?
Vector should be 0.
Okay. So this will give you what n-1 equations. And what do you think is the solution of this? So what does it mean? If you take the exponents out, yj is equal to Equate this to B over. Right here, potentially, this is true for all j, going from 1 through n minus 1. What does it mean? What is the only solution of this system of equations?
Very expect. If by the you will follow either by primitive.
That y r star should be simply square. Volunteering is more than 14. And all of these will give you just n such. And the only solution is by. Okay, so what is the punchline? Whatever I achieved by doing this. Its summation yi is some number always. What is it telling me? That whatever that s is, this quantity is minimized when y is allowed s by n. What does it mean for my function f here?
Okay, so in that case, there will be a coefficient -1 plus 1 by n outside. And that will be so we can write the minimum value of that will be 1 by n minus 1 into e to the power minus 1.
This one.
Yes. Into e to the power,
All of this.
yes. Summation yi by
What is y already has.
yes.
Expression y is just s. Okay, so let's come this and as in place of this. Is that correct? What is this minimum value? Just tell me that. For whatever fixed n it is. What is the minimum value of this?
And into the power.
And into that.
That's all you got. But for fixed from. Yes. Then I will multiply that. Okay. Just use this. To conclude whatever you want to conclude. Then go back. To what I can do. Yeah, so there is some fixed value, right? There's some s. This is true for every s. Somebody work by line. But just by differentiating, I'm able to prove MGM inequality. I don't have to go back to many other different proofs to MGM.
So the maximum is at n when all of them are equal.
I don't necessarily need it. All I'm doing is a very equal. So as long as I can show that this quantity minus this quantity is greater than equal to 0, which is what I've done. All you have to show me is that that is for any s greater than equal to 0.
We've seen that the minimum value is greater than 0.
Yeah.
And so every other value, every other difference will also be greater than 3. As in this thing, we write greater than
This is the whole concept. All I want to show is greater than equal to 0. Yeah. For whatever s this is, I got the minimum value of this. Why can't I just subtract that? What is that quantity? So overall, is nothing to this quantity minus n times e to the power n by n minus. What is this? Minus e to the power s by n is. What's happening here?
There will be a value positive. Okay. Then you go to serious. Yeah, there is a by here.
This. Yeah.
Zero.
Minimum value is
Is everybody using? All I have used is the net optimal value to the equators. That's all it is. So don't get stuck up that all we are doing is minimize f of x. You will encounter all sorts of interesting problems for which you can use what you do. All you have to do is to just rewrite them in a certain way, so that you can. We'll come back to this at the end of the class, which is another set of necessary sufficient conditions. And try to see if you can even get, even without all this, much faster. Okay. Alright, so now, carrying on from last time, we will do the now restrict ourselves to convex function. Last time we did not instantiate anything. So unconstrained arbitrary functions. Now I'm going to say. Oh. At the moment, I don't even need FTE counts. But if x star is the local minimum, then so what was your guess for the condition? Now, x is not necessarily all of R. So clearly, this is not necessary. And at least that you should appreciate. Is everybody okay with that? This is not necessary. Can you give me an example? When x is not necessarily all of R. Anything will work. Simplest thing will work. In f(x) equal to 1. Pick the simplest function. What is the simplest function you would like to?
X squared.
Oh, yes. What's the simplest convex that you would like?
0 to 1.
So what is the minimum? At what point it is achieved? Okay. Is it true?
Yeah.
Now, what's the first non-trivial step you would like to take from Kyle? To suppose. 1. Putting on. Is this true? Where is the minimum and is this true? Minimum definitely is 1. While the derivative runs clearly not there. So this is at least everybody should appreciate that this is fast. So what should be this? This work will be done and try to tell me a condition which will be necessary. Everybody on board? Okay. Part of interest. What will happen at one? What is my application? So looking for a condition in terms of the gradient.
Local minima, we need to check for the interior points. The points not on the boundary. Or that close.
Simplest function, simplest convex. Very complicated.
The,
You know that minima is at 1.
the slope will be greater than 0, right? Because it has to increase. If that is a minimum, then every point.
I think, yeah, keep going. So what is the why did the gradient becomes zero in unconstrained case?
Because in the uncon
Because it was lower than all its neighboring points.
Correct. So use the same logic. Now the fact is, your boundary will not allow you to go in certain directions. So what should happen with respect to points within that constraint set, forgetting what is happening outside of it?
In the available direction, the gradient should be positive.
Okay, so how can I state it? I cannot state, right? F of del of x star should be greater than 0. That's not how I should state that.
If on that interval, the function is increasing strictly.
How should I go volume on checking it?
this slope will be
From increasing the functional value is
Give me condition. What should happen if the point is an optimal local? Just take this example, you don't have to go anywhere. Function is x square, interval is 1, 2. What is so special about 1?
it's a boundary point of the domain.
But that's not capturing anyhow the fact that gradient is something else. I could clearly make a function, just shift this function by 1 unit and make 1 to be not the gradient, but
So
1 remains the gradient, 1 remains the boundary. So boundary point cannot be a condition that optimas happen at the boundary. That cannot be true.
the f dash is greater than 0 on that interval.
Why will it be greater than 0?
1 comma 2.
Either you give it for this particular case, okay, or give me a general condition. Don't confuse between the two. What's happening at 1? It's a boundary point, but that's not clearly sufficient. Because just by shifting x square by 1 unit, clearly 1 will no longer remain the boundary point. Right? 1 will remain the boundary point, but not the optimal point. That's clear? So boundary point is not the necessary condition. But with respect to any other, what am I asking? I'm asking, suppose x star, which is my 1. All I care about is all the points lying in this interval. I don't care about the rest of the world. What is that condition? So take any x. Will ask you. X star by definition will work in x. And I have del x. Just in terms of these 3 points, you can give me a condition.
The slope of x, like a slope of f at x star, x star is the minimum gradient.
If x star is a local minimum, something should happen.
The slope of f at x is c greater than
Greater than what?
160. The thing is that
So del f of x star less equals to fx minus fx star by x minus x star. Then fx minus fx star by x minus x star.
This is the derivative. What is this quantity?
So this is the chord. So if I take any other point other than x, so this is the chord joining x and x star. Slope of the chord joining x and x star. And that is the slope at x star.
So, what is the definition of del f x star?
Yeah, the limit of that basically. So I'm saying that slope will be decreasing if you just slightly move from there. The slope will be minimum.
Give me this function. Now, whatever you're saying is that correct?
No, x star is the delta.
Yeah. Means
second derivative is always
I just made a different function.
Yes.
All your conditions still hold or not? All I did was just shifted this by 1. I don't actually understand this. Anybody else?
Yeah, so the slope of the thing is like it's a convex function.
Okay,
It's not that, it's not convex.
not necessary.
So the gradient along the direction x minus x star is non-negative.
Okay, why is that? That is at least more reasonable than this. You can give me geometry is also that is me.
Because along every direction from x star, the function should increase.
Yes.
So the syntax is convex any point x in fact.
Let's say this is my x. This is my x star. What are you saying? Then at x star. Multiplied by one, x one, x star, x one, shouldn't be. It's the direct. Yes, what is it? This is greater than equal to 0. This is greater than equal to 0. Why is that?
Okay, then the function will increase along the direction of x.
With inequality implies that. What is this term? Left hand side. You've done this. In a convex function, what exactly happened? When we said some inequality, that let's say this is x, this is y. For x is one plus 1 times. What is this quantity? Which is using along the gradient, how far is he walking? Okay. And what will happen? Short. For a convex function, then it's equal. What is this quantity? Therefore, y plus what went here, and that's what this is. Therefore, y plus quantity in this direction, we started to walk x minus y or y minus x minus y. So, where is that value? Side here. That's this right hand side. Okay. What is this right hand side? In this picture. Where should I put it?
The point on the tangent below x.
Yeah. So I'm trying to this direction, this direction, how far I'm walking? 5 seconds. Still I'm below. That's exactly what this was. Okay. This is exactly what he is trying to use. X star is here, x is here. What is del f x star of x minus x star? Along the direction, that much I'm walking. What would happen?
Below the function.
Where is the function coming from?
If this is greater than equal to 0, then we know that f of x minus f of x star is greater than equal to 0.
Okay.
So then we will have that x f of x star is.
So that the equations will work themselves out. Still this picture, can you tell me what is it? or rather what you expect to happen is being represented by this. What do you expect? That's the most important thing in calculus. If I have a local minima over a constraint set, what condition should I satisfy? Let's do suppose then it's for some x. What will happen? Can you prove that x star cannot be open? Let's do the reverse. That's alpha times. Why? That take what is this quantity equal to? This should be done multiple times. Oh, now that is less than equal to 0 for some x. What can you conclude from?
There is some storage that must be less than 0.
There is difference of
Because the limit is less than 0.
Because
The limit
I
is
assume that there exists an x for which this quantity is less than 0. Okay, so
so then there exists some alpha for which this thing, not the limit, like I hope that alpha exists.
yes, so
so the eight part is smaller than the alpha is small in the
alpha x less than of x. What is the quantity?
the x star is the probability.
So with the counter positive, what do you get? That if x star has to be equal to 0, this has to be greater than 0, greater than equal to 0. Now can you use this to show the graphical argument? Is this clear?
Have we established that it must also lie in the domain? Like that?
That you can, because of the alpha, in whatever direction you are allowed to.
Okay.
So that's why, in which way you are allowed to go, that's what it is. But there exists an x, so there is some alpha. So now can you use this to be the graphical argument? Everybody happy with the proof? Right? Proof is 2 lines. We go to contrast a little bit. Proof is 2 lines. So what really happened?
So we are clearing that at x star at a local minima.
Yeah.
So locally,
You will just follow these steps and just tell me. That's one way of building it.
locally for any x,
So suppose it was less than 0 in some direction. In particular, let's say there was some x here at which it was less than 0. What it's telling you is there exists some point in between at which the function value will be smaller than x.
in this case.
This is yeah. Right. So, okay. Okay. One is the local minimum. What should I go? And suppose the condition is false. There is a condition X.
I have some doubt in this.
Right?
I have some doubt in that.
What are they?
So for some x, you can say that, and for some fixed x, you will get a fixed alpha such that it is below x f of x star. But one can ask that if we go, if we take more smaller neighborhood of x star, then it might not. Means if you don't choose a simple.
What do I have to prove?
No, I'm
If
saying-
this is less than 0, then X star is not local.
Yes.
I'm not showing anything more. And if you do the counter positive, A complement implies B complement. What happens? If A complement implies B complement.
Yes, sir.
You say nothing more. Okay, so now there is an X at which this point this is false. What does it mean? Victoria, where of it comes from there. What does it like being less than 0? What does it mean?
The slope over there is the
Slope from one side.
slope of y. Because x is greater than 1.
X greater than 1.
So then that x minus x star over there will be greater than 0.
Yeah, let's call it. So X is greater than 1. What is the X star?
The slope at
No, we have the function. We have a function which is x squared. Then 2x, 2x. 2x there, 1. So 2. 2 times x minus 1. Suppose there exists an x for me which is less than 0. Does it even exist as a question?
not in this way.
Not in this group. So what I really have, that's what you should check. Very important to develop that. To see what I've written is just a manifestation of what the insight is. Who's played? Who's played everybody? I did really think very important. And make sure that you come with some insight in next class. We'll actually discuss this before being in next class. Okay? Because if I tell you something, it is less likely to stick rather than you generating your own notation. Okay, what did we get? If x will convex set and then be some function. If x star is local median, then star times x minus necessary condition. When did it become sufficient? Can you give me an example that it is sufficient? in the int. Convex function, what happens? With inequality, always. So this is greater than 0. What does it mean? F of x is greater than f of y. So y is local minima as long as 6 is greater than 2. That's all. That's one language. Then it's a very broad function, sufficient for convex. Insisting on local optimality for the moment because we want to soon say that local optimality implies something for convex function. Do I need to write a proof? With just one line. Directly use your gradient inequality for the convex. That is directly gives it. Can we go back to arithmetic geometry inequality? We want to show that this function is greater than or equal to 0. Now we learn something. Right. Here we have to rename this parameter so that you will do unconstrained objects. But now we know how to do constraint optimization as well. Right. So if I constrain the summation yi to be prime on a y, so summation yi equal to x, that just defines the convex set. Everybody agrees. On that convex set, I'm trying to minimize this function. What are my necessary and sufficient conditions? Also convex function. That much now we know. The function we are trying to minimize is this subject to summation yi equal to s. So it's a convex function with a closed convex set. So what is my optimality condition? I can directly apply and get an answer.
The gradient of
Yeah, the gradient. Everybody agree why I have to do circus? Because I did not know how to do the constraint optimization or necessary and sufficient. Now that I know that the function is convex, constraint is summation yi equal to s, I can directly do it. So solve this problem by evaluating sufficient. This only sufficient condition minimize some of these e to the sum. E to the yi for summation people outside. Then doesn't matter. So what should this answer be now? Remember this is sufficient. See, this is also giving another handle. You can guess and prove. Suppose your guess was x star is s by I. All you have to do is to show that that inner product is greater than or equal to 0 for all x. Suppose I could just get that the optimizing yi star is such that is equal to s by n. What do I have to check? That gradient, let's call this g. Gradient of g at s by n times y minus This is one. Is greater than or equal to 3, that's all I have to check. Okay, then we'll take it quickly by this. What is gradient of G? Usually, it's just e to the power x is e power x. So all this will be shown with e power s by n, e power s by n. Pi minus this. I just need to check whether this is true or not. Is this true? Any point which satisfies this, that's all I need to check. Overall points y such that summation of yi is equal to s. This is beautifully open up, that's the point. Because when I take the inner solution, what will be the product? Each time we're getting multiplied with the same quantity. So e to the power is by an outside.
Why are you?
Now, there is a constraint to be yes. And this is exactly the same. So this quantity is identical. This is the power. You're building up more and more power, make sure that you use everything you have at your disposal.
But that this is coming from the last one, right?
This is coming.
The last sector that we tried to do.
What did we do there? I have to do unnecessary elimination of a variable so that I can bring one unconstrained set. Here I don't have. Even if the constraint I can do that. That's the power. And here also I'm using the file that this is the convex function for the fitness sufficient. Okay. Yes. Forward. First of all, you should understand the statement. Then write the code.
The first time we can go by contradiction, assume there exists, assume that it's not a global mean. Okay. So then let's say that x star is a local mean.
You don't need the proof. Just try to understand what it's saying. And again, give me an argument or an intuition as to why this should be true.
The thing is that
Proofs will not be difficult. That's the funny thing. Proofs are 1 or 2 lines. Point is why something should not. So you take a convex function, look at its local limit. What is so special about that?
It is that the gradient condition that we have here. Okay. So the gradient the dot product of the gradient and y minus x is always greater than or equal to 0 because it's a local minimum. Okay. So like that is true for every x. So I think that's why x is a minimum point. So like it's true for every x. Then it must be because if it's not, then you have that for some y this dot product is less than.
Trying to give a proof.
I mean, I'm trying to visualize this.
Yes, did you only the visualization? Don't give me.
If we have more than one global minima,
Yes,
since by definition they both have to be equal value.
yes.
The chord connecting the two global.
That's all you should really visualize. Suppose there are two distinct points which have the same global minimum. What will happen to points lying in between? Because the function is convex.
The chord should be above the function.
Yes.
So that should be even lower.
So the function values between should be even lower.
That's all. It's much easier to handle it those ways. Rather than prove side by side, they're not difficult. Okay, the second one. I'll write a proof also for both of them, but I want you to think about it first. For some reason, I lost it in my notes.
For the strict case, that E equal to will be strict inequality.
Which is called.
And that where we are going for, given x star is the local minimum, we are moving towards the direction of x in the gradient, x minus x star. That del end of x star into x minus x star get equals, so that's inequality should be strict.
Okay.
So if there is not global unique minimum, then we can choose another x prime, which is also global minimum, and we can just use the both of them in the same instead of x, we will use x prime. So we'll see that x for the x prime, if x star into x prime minus x star is greater than 0, and also for the x star it will less greater than 0.
So, true. Then, where is the uniqueness proven? For it to be unique, what do you have to show? That if there is just another point, what happens?
If there is a second global minima, then the chord joining the two should be, because of the strict condition, the chord should be strictly above the function. So the function values on that chord are smaller than the global minimum. That's a contradiction.
Okay. Both proofs are identical. Any difference between the two proofs or they are identical?
Besides the strict conditions, they are.
Okay, so where is the strictness being used?
So
If it was not strict,
what will be the
what would not work?
The uniqueness will not work.
Okay. Give me an example.
Constant.
Very good. So the function remains constant. What is the global minima?
Every point is.
Every point. Now you want to make it strictly convex. How do you make it strictly convex?
if there are two global minimum,
Your constant function. I want you to disturb it and make it strictly convex. What will you do?
I just put it down so that there is a group.
Okay. But Is it okay to bullet one point? No, right? That won't make it strict convex. What do you have to do? What kind of operations you have to do to a constant function to make it strictly convex? There's no trivial operation. You can just simply pull one point down. That won't make it, because wherever you're pulling it down from, you have to essentially somehow make sure that the weight is associated with every single point. While I'm pulling this down, everybody else is also shifting upwards. It's not just purely sufficient to put one point down. Yeah. Oh, so that's right.
Also, you're not giving the reference difference. It is not necessarily differential, right? It's just for any of that is correct. Right?
Yeah, for the moment. You want derivative. We'll see. We'll prove. The same proof. Whatever. Proof is a proof. All I want is that you prove it. Prove it.
Let us assume that there are 2 points, there are 2 local minimums.
No, I'm not saying uniqueness of it. That XL and XG be local. And global. Right.
Now, we don't have the local minimum. We need to show that they are global minimum.
So here, however you want, I will write what you use. If you don't like this, I can change it.
So since F is convex,
You have some part L, XL, the local.
since the F is convex, the F of lambda times XL plus 1 minus lambda times XG will always be less than equals to. It will always lie in between the chord joining. Since this is true for any lambda in between 0 to 1,
Yes.
for for every neighborhood around XL, since XL is a local minima,
See, I don't know what promise you started with. That's the problem. It would be easiest if you said, let XL be a local minimum, but not a global minimum. That promise would help you what you're doing. If this is the promise, it's going to be complicated. If you want to change the promise, or you want to continue with this. I'm not saying this is wrong. What I'm asking is whether you want this or you want something else to start. If we keep going down this path, what will it go?
so that like XL will no longer be a local minimum.
Okay.
Because every time for any epsilon neighborhood of XL, we will find some points that functional value will be less.
So carry on.
So f of that is less than equals to this. Hmm.
What do you want? You want to find a smaller lambda, such that what else?
Such that like for any
So it will be smaller than f of x, how do you find that?
f of xl is less than equals to f of xg, since xl is a local minima and xg is the global minima.
Xl is larger.
F of xl will be less than f of xg.
What does it mean?
Global minima will, f of xl is larger, yes. So that point will be less than equals to f of xl.
What is this?
Yes, the functional value of that thing
Yes.
will be less than equal to f of xl. F of xg is less than equals to f of xl, right? So the right hand part will become f of xl. And since this is true for any lambda in between 0 to 1, we can say that we can move to any small lambda to the right of xl, and we will be getting the functional value lesser than that.
What have you proved on this?
So I have proved that xl cannot be local minima if it is not the global minima.
Distinct. If they are distinct, is what you do. Use lambda small. But what about level equal?
Here we will be only getting less than.
Why is it okay? To disprove, we want strict or not?
See, if it is equal to them, we are already getting that it is the global.
No, but what have you disproved here so far? All you have created is a point close enough to XL, at which its value is the same.
Yes.
Why is it disproving the fact that XL is local? What's the definition of local?
We can find in
A neighborhood.
neighborhood such that the functional value at that point is less than equals to the functional value.
So you're not disproving. All you found out for me is another point. Close enough. You go lower. You go lower. Okay. Is the problem there? Why this is not sufficient? What have you proven? That there exists a point close enough to XL with a value equal to XL. That's not good enough to disprove that XL is not equal. So now you do whatever you do, quality has been strict.
So for if every lambda will be getting that less than equals to, then that value will be equal to the global minimum. The functional value will be getting at global minimum. So from that we can say that local minima is.
But what was this quantity? The global minimum was different. That is inequality, not type equality. What is f of x with respect to f of x?
F of xg is less.
It's not less than equal.
Yes.
This already I can take it off. Okay. Because f of x is by definition a global minima, while x is only a local minima. So better be that f of x is strictly less than f of x. Otherwise, what's the difference? Then you can create a point disproving the fact that x is not relevant. Okay. Will be fun.
I thought a different.
So we'll do that some other day. Even my time I want to do something else also. So B is strictly correct. Supposing there are two global minima, that's the only way to start. Okay, so let's say xg1 and xg2. Now supposing the function is function and on back what will happen if I take xg1 plus xg divided by 2. So what is the function evaluation of f of x? Is smaller than f of x. Somehow I have to claim, given that these two are distinct points, less than 50 less than zero. Then it is true that these two are two distinct. But why is it true?
Xg1
It's still a convex it's still a convex
Yes, so it belongs to x, yes.
Yeah, and then since f is convex, f of x d1 plus x
So
d2.
f of x is again equal to because of strict convexity. This with one half of xg1 plus f of xg2. This is where one half is the real result. So take any other linear combination. These are identical values. And then it's strictly less than 4x. So if there are two of them, then you can look at a convex combination of them. You actually get a value even smaller. And that's the convex. So this is identical. Okay, so now come to the most interesting part of it. Something about projection, some actually one part of it would be number one. It's really good for what we have learned. So minimize it's so what are you given? You're given a point Z. It's come convex at X, and you project it. That's what is minimization. You prove something in your homework one. And the prediction is unique. So we're going to prove 4 parts of the prediction. Including all that we have learned in last class. So this is a nice convex one. That's why. Let me call the projection as projection of Z as Z plus. Wherever that is. You could index it with X, but for the moment, let's keep this. For every Z after that. X star is equal to Z plus 6. Very. So define G of X equal to X plus continuous function and non-response most important. Okay. We will take 2 points and look at their projections. We will not go continuing the this is also very interesting that if X is in fact a subspace, it is not necessary that every convex set is subspace, but if it is a subspace, then star Z plus Z minus star perpendicular Z star. So start to observe a lot of things. What is going on and how will you do it?
What is X star?
Which is representing X star as the optimizer of the optimization problem, is also represented as Z plus. The X star and Z plus both are points in the convex set X where Z is projected. Z is the point I am projecting. Okay, now whatever we have done so far, you can knock off saying this implies this implies that, this implies that. So let's look at A. Why is
So
it?
we have to prove all the results. Like,
Sorry, I forgot. Projection here. What implies part A?
The global minimum is minimum is unique.
No, which whatever we done so far, it's a strict convex function. What is a strict convex function? Z minus X whole square. It's a strict convex function. That implies that Z plus is unique. That's simple. Once you develop all the machinery, certain things will follow quickly. So part A comes directly from the strict convexity of Z minus X whole square. That's all. But what about part B? It's reminiscent of something. We said something about the function is convex.
the gradient of X star, X minus X star, the equals to 0
Okay, so what is the gradient of X?
is 2 into Z minus X.
So
Yeah, so
And then it's a global minimum point depend on the delta trans then with the dot product of the gradient and x star minus x star would be greater than or equal to 0, but so
just invoke whatever you do so.
but we also have that it's also equal to x star is equal to z thus.
But that's the definition. I'm using X star. I could equivalently use Z plus. That's the same thing. They're not different. Is it confusing? What is there? It goes to X star equal to Z plus. There's nothing different about it. Just writing it in this particular. X star is the optimizer of this. And there is the point going there, it's just Z plus. It's very equal. So where is this coming from?
The gradient of,
What are the words?
yeah,
Yeah, this
If X star is the local minima, then this better be true. Yes. Okay, so what should I do there? The condition should satisfy. So what is this quantity in terms of the gradient of it?
Negative of the gradient.
Okay, so what's that?
So this term is positive.
Mhm.
Okay, so since this term is negative of gradient and the overall is negative, the gradient itself is positive.
So what's my condition? Very. X minus X star. Wait, that's what my condition was. What is my X here?
was Z minus X was first.
That's all I got. Yeah, right, is that there? What is there?
two times.
What did I do?
That thing should be greater times X minus X, that would be greater.
Okay. So
So
applying that, what do I get? 2x. What other? At X star, so I get this X star. And then it's what that is. Multiplied by X minus. That's necessary. Sufficiency will come from this. Sufficiency will come from where? Option is convex. It's also sufficient. That's what we get you.
Right.
So now comes the most interesting, the non-expansive property. Why do you think what is that?
Can I go to
Non-expansive. That once you project, so you're projecting Z here, you're projecting let's say Z prime somewhere else, which is Z prime. So Z plus and Z prime plus are no more further away compared to Z and Z primes. Why do you think that? This is a very critical property, keeps getting used all the time. The projection onto convex sets is non-expansive. Do you think it's true when the set is non-convex? Give me an example. The set onto which you are projecting is non-convex.
yeah,
Can you make
it
it?
might be false.
Give me an example.
If we take a non-convex set where we have a V-shaped gap,
Give me a non-convex set.
take a pentagon with a V-shape once. Yeah,
Okay.
yeah,
So this is set. Let's say this is my set.
yes.
Okay.
So we can take the midpoints of that each. Yeah, and take 2 points outside so that there are the projections.
How do I do that? This point, there is no unique projection first of all.
Yeah,
There is no question of expansive versus non-expansive.
no, you can take farther away.
Here.
Yeah, like not in the midpoint, I'm saying.
Here.
No, that those points will work. I'm saying not take the there are perpendiculars that joining a single point, right?
Yes.
Yeah, don't take the intersection. Just take little bit farther away.
Here.
Yes, and Also,
point,
yes,
is another point.
yes.
Okay, what happened? Here they were close. Their projections are further. So clearly it's not going to happen. Now what is the magic in the convex? Why is it happening? So both should be clear. If I insist on the function to be convex, said to be convex, what goes wrong now? Both should be simultaneously clear. Then why do I need it and how do I actually use it? I need it definitely. But now the fact is that given is convex, why should this be true?
Can I say for a particular case? Yeah. So if you have a circle,
Yeah.
centered at origin, we can consider rays y, what the rays is going from origin, right? So any 2 point outside taking outside the sphere. So if the projection will be along the rays,
Yeah.
and always the distance between the rays is as we are approaching towards the center is going to.
Okay, that is very specific to a circle.
But for the convex set also, yeah, near.
What number is it? Where? There is no such thing.
Yeah,
So
I mean, in that case, it will be like constant.
fine, but whatever you're saying, you can't keep changing in the shape of the convex. It has to be property of the convexity of the circle. So why is this not possible is the question. You can even think of it that. Then why convexity saves you from something like this? Yeah, it is this and this, not like that. Like in fact, it's fine. Okay, let's try and go this. So from the previous part, what do I need to come? B. We have x minus x plus x x plus times any w belonging to. So w is so we are coming directly from part which you have proved. Okay, how do I use this? We want to look at y. It's going to get to the table y plus. So candidate w is y plus because y plus also belongs to inside. Let's see where we will place that. If something is not clear, stop me. Y plus. By definition, that's the projection. I'm just using that. Okay. Now reverse will also I can do symmetrically. So all x's can be replaced by y's. That's all I is necessary.
And now if we take the negative of this, we get y plus minus x plus on this side. And if we take negative and this thing will just become greater than x, given that is minus 3.
If I add it,
We can just use that.
no more technical results in here. Now it's all right. Suppose you add them up. What will happen?
It's still. It will be less. We have a multiply x, so we can take a common out.
Okay, what is the common out? This is common with the negative.
Negative sign.
Okay, so let me make sure that I can do that. So x plus minus y plus 1. 1 3 5 minus. It's 5 minus 7. Is
Very good.
okay, sense. Okay, now who sees the answer? What do I want to prove? The norm of this is smaller than norm of x minus y. That's all I want. we clear what we're trying to do. I'm trying to make sure that the distance between x plus and y plus is no more than x and y. That is essentially this norm is less than at most as much as x minus y.
We are adding the negative of the second inequality.
Whatever. We're just adding, no negation, nothing like that.
But that inequality, we are like -1 is being multiplied, right? Before it.
This is a minus here, I'm not multiplying it,
Okay.
just adding it as it is.
X minus x plus minus y plus the vector.
So what are the good terms? This multiplied by x minus y. That will exactly be the norm.
No, yes, another,
And what will be the remaining?
it is a non distance.
There will be some cross terms also. What will be the cross terms? So this implies that x plus minus y plus whole square is some common terms. What are the remaining? Will come to the right hand. Okay. Is equal to x minus y minus one. Okay, now I can use whatever you know.
That is less than the product of the environments.
That. And then one norm will divide this. Okay, which is the one for you. Norm of x is norm x plus. We'll divide this in the way. Everything is substrate. Oh, what is subspace? You can remember the definition of
Vector subspace.
yeah. Subspace, subspace. Even one line is also.
Very good for different.
What is the substrate? First of all? So let's say subspace is x. So if A belongs to x belongs to x, then what is belongs to x?
I don't know, this lambda x belongs to it.
Okay, what else?
X plus y belongs to x.
And if it's all I don't know. That's all I get. What all I wanted to prove. Exactly instructed. Then now it's precisely perpendicular to the subspace. Z minus x star. So where I'm projecting Z2. This set is a subspace. Then for every x sitting inside, that vector is perpendicular. That's all. You learned this many years ago, I'm pretty sure. That or projection is orthogonal. Yes, but that's only true when the space on which you're projecting is a subspace. That's what we're trying to do. You can give me a proof. You can use part B. Every time you're trying to prove some equality equal to 0, all you have to do is to show less than equal to 0 and greater than equal. And this is given to you from B. So what should I evaluate these things at is the question. So what does subspace mean? If x and y belong to subspace, just come in.
It will be
So also it implies x minus y also belongs to subspace. That's all you have to do. Use 2 points and evaluate this as x plus y and x minus. Is it okay? What to do it? Oh. Now that's the x star on x. Then I know that x star plus x is belongs to as well as x star minus x belongs to. From part B. Get z minus x star times x star plus x minus what? X star. X star. I'm just substituting for an arbitrary x as x star plus x. See, this is where I'm. Is this true for any convex set? This is a special property I'm insisting because of the subspace. Because it is a subspace, I can do this. Convexity will make me do lambda x plus 1 as lambda x. I want to put both lambda and 1 as 1. And this is the limit of the polynomial. Similarly, same thing, x star minus x star. This also. So what do I get? I get z minus x star into x into 0 and z minus. Let's start. Way ahead.